If you're having to watch this from home, it's 2/7/25 Friday. It's the weekend of the Super Bowl. So you have to watch this video if you need to. Springs and pendulum speed turn in, some wave drawing practice. And now we're going to look at what waves can do that particles cannot. You've heard of some of these before. Some of these may be new to you. But I'm sure you know that waves can reflect. You may have heard of something called refraction before. Just quick show of hands. You've heard of something called refraction. Any applications you can think of that rely heavily on refraction that you know of? Applications, wave related? Okay, no one's willing to say anything, but one of the things would be optical lenses, like the lenses that you wear for corrective lenses. Those are based on refraction. Diffraction, raise your hand, you've heard of it? Okay, just a few people. So we're going to look at these. Now there's others than these three, and as a matter of fact, I only got through refraction in my 5th hour, so that's where I expect to get with you guys as well. I'm in your note packets, and at this point, we're going to start looking at things that particles do that waves cannot. Now, particles can reflect just like waves do, but the particles are a little bit less restrictive than waves. So I want to look at what waves do when they reflect. You've played billiards before. Have you guys heard of this law that whatever the angle a ball hits an interface at, it's going to bounce back at this same angle? Have you heard of something like that? It's called the angle of reflection. Or the law of reflection. If you haven't seen that before, let me draw a little diagram down here. If a particle is moving like so, and it hits a boundary, and it hits that boundary at a certain angle, that angle may be theta I. If it can't go past that through that boundary, just hit, and it hits at that particular angle, how would it reflect, you think? Exactly the same angle relative to the normal line. That would be theta r, and it would reflect right back off this way, and it'd go that way. And so particles do that. They behave by reflecting, obeying this law of reflection. Waves do the same thing. If I were to draw a plane wave, I'm going to do that off to the right. If I were to draw a plane wave like that, it's a little bit more complicated because waves are more continuous. I would draw a normal line. That normal line is perpendicular. And let's say that I have a wave that's coming in like so, and hitting this. When it hits this thing here, I'm going to go ahead and draw one of these up here. I might have a wave velocity vector that looks like so. And when it hits, it's going to reflect at the same angle that it came in at, and it would go off like so. And so because it's a continuous wave, it would look something like that. So that would be wave reflection. Particles behave very similar to that. There is a key difference, though, between waves having phase relationships and particles not having any phase. If a wave is traveling along a medium and I have a fixed endpoint, if it's fixed, meaning the endpoint of that wave cannot move, it's fixed in place, then the waves are going to reflect inverted. We're going to get a crest would turn into a trough. Another way to say that is that it reflects out of phase. So we would have a phase inversion or an out of phase reflection. So the phase would flip. Comes in as a crest, it leaves as a trough. That'd be a 180-degree phase shift. Particles aren't wave-like. They don't have phases associated with them, so we don't worry about that. If it's a free end, so a free end would mean that the endpoint is free to move, it's not fixed in place, then it's going to reflect, and it would reflect upright. So it would not do a phase inversion. We would say it's in phase reflection. 2 examples for you, one for each one. I've talked a lot about stringed instruments, and I don't think there's a lot of people in here that play the stringed instruments. There's other kinds of instruments that people have played, but a guitar string acts as a fixed endpoint string. One side has I think it's called the bass, I think. Anyone know for guitar where all the strings come together? The bass? The bridge. It's called the bridge. Is that what it is? Yeah. Regardless, the bridge sort of acts as a fixed point for those waves, or for those strings. And then the other side, the fret, the fingers go between those frets and it sort of locks the wave or the string in place. So it acts as a fixed end. Now, pier, let's see, the water reflecting off the pier. And let's see, Elena, exchange student from Spain. Have you been to our pier in Grand Haven? Have you been there before?
I don't think so.
Okay, so pretty cool. When the weather gets nice, get out there and see it. But when the water reflects off the pier, it can ride up the pier and then reflect offward. And you may have seen some reflections that look like the drawing that I made down on the bottom right, but it would reflect in phase. And so it depends on the terminal endpoint. Now, I don't know if I showed this to you before. I think I did. Let me just show you that phase inversion with this thing. Okay, so if I have a, let me do a pulse wave. I'm going to put this in slow motion. And so the pulse is just going to be I believe it's just going to be a triangular wave. That C clamp on the right, so called because it looks like a D. No, when it, I have damping going on there. Let me get out of that for a second. Let me reset. Pulse, no damping. We don't want to have any damping. All right, so let me do that pulse. There we go. Oh, that's really fast. All right, I'm going to slow that down. So as that thing hits that C clamp, you notice that it does a phase inversion. So that C clamp is locking that green particle in place. You might think of it in terms of Newton's third law, that if the medium itself, if the wave is trying to bring the medium up, when it tries to bring the green thing up, the clamp says no and it pushes it back down. So it inverts that. Now, if I did a free end, a loose end, I'll wait one moment for it to be able to do that. If I did a loose end, then we're going to allow that medium, when it gets to the end point there, we're going to allow it to move. And so when it does that, it reflects in phase. That kind of phase inversion, or keeping the same phase, has a lot to do with like musical instruments and whether or not you get a certain kind of note played on, whether or not it's a saxophone or it's a tuba or a clarinet. It has to do with what kind of endpoints we have. So reflections for waves can be more involved than particles. Okay, so a little visual for you. I don't think you're going to struggle too much with reflection. The one that we're going to, well, you might struggle a little bit with this. This is called a reflection and transmission. Often we meet waves don't hit a fixed or a free end. What they hit is an interface. They hit something that changes the propagation speed. It could be a light section going to a heavy section. Let's draw some things that we looked at from yesterday. Would you guys agree if this is V over here, that this would be V over there, that if the section becomes more dense, that it's going to be harder to move that energy through that new medium and have more inertia, the speed would decrease? So we have an interface. That interface is not an abrupt end, it's more of a discontinuity. It's something that changes from one kind of medium to another. If there's a change in speed, if the speed changes from one speed to another, we're going to get some sort of reflection and some sort of transmission. The reflected wave here, you notice that this thing here sort of acts, this discontinuity sort of acts like a fixed end. It turns out if I lean too close into there, it picks up my shoulder and it doesn't quite. That's acting as if it's fixed. It's not perfectly fixed because it is free to transmit that wave into that new medium, but because it's going from a light section to a heavy section, I'm going to get a phase inversion on the reflected pulse. Now, if I were going the other way, if I had a wave traveling this way on that, I would go from a low speed to a high speed, and this would act, that interface would then act like a free end, and you would see that it would reflect the wave sort of in phase. Now, I'll show you a visual of that coming from this guy. So here we have, again, that wave traveling along. Oops, no. Let's try that again. Okay, so here we have that wave traveling along. It's going to hit a hard boundary. So again, this is just another visual of the same thing I showed you from the FET simulator. Here's a soft boundary. Here's more of what happens with an interface. So for this one here, it's not a perfect endpoint. It's something, in this case, I have a lightweight medium that the incident wave is on, and then it hits the heavyweight medium, and the reflected pulse is out of phase. So any discontinuity between the left and the right, with the speed changes, you're going to get something to reflect and something to transmit. Now that's going one way. If I had the other way, here what I have is a heavyweight medium where I've got a short wavelength and stuff like that. It goes into a fast medium. You can see that the wavelength increased, but the reflected pulse was in phase. And it has again to do with which way that wave is traveling. So this is more what real waves do. We don't often have purely fixed or purely free ends. We usually have just interfaces. Common example of that, warm air going to cold air. Oftentimes there's like if you've done any, or you want to do any scuba diving or something like that, thermoclines, raise your hand, you've heard of it? Thermocline, sort of like an abrupt change in temperature. That can change the speed at which waves sort of move because it's a speed dependence or temperature dependence, and that can serve as an interface. Any change in speed will result in some partial transmission and some reflection. Okay, so waves can reflect. The one that I want to spend the most time with you guys today is this thing about refraction. And so refraction is where waves will bend at an interface. They're going to change their direction of travel. If you wear corrective lenses, how those things work is based on light changing speed as it goes from air through that lens. And so the amount of refraction depends on the angle at which it hits. So it's the angle of incidence. So what's the angle? And how big is the change in wave speed? So if there's a really abrupt change in speed, or you have a really oblique angle where it comes in at a really large angle relative to the normal, you get a pretty big change in the direction. Now, what I'd like to do with this is I'd like to help you build a sense of this by using a little bit of you as a model, walking as soldiers, arm in arm. If you wouldn't mind trying this out in the hallway area, just so you can sort of see how waves might change their direction based on which way they hit an interface. So when we do this, I've taken you guys out into the hallways before. We can't be out there for too long because we have a lot to cover, but if we have enough people to be able to do this, I think we do, 4, 8, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, that's just right. We could do 5 groups of 4. So even though we don't have, you guys have 4, you guys are 4, we could split you guys up there, you two. One of you with that table, another one with this table, and then you guys are going to be like soldiers in a line. If you could do that for me, I think it will help you understand this refraction idea. So what we're going to do is we're going to go out this way with your elbow partners. You don't have to walk arm in arm right now. So when we get out there, you can be arm in arm. So out through that way, this way, out through that way. This way, out through that way. This way, out through that way. Liam, I need 2 meter sticks. 2 meter sticks. 2 meter sticks. That would be 2 meter sticks.
Oh, 2
Yeah, 2 meter sticks. So it's 4 meters total, but I need them as 2 long 2 meter sticks.
Thanks, Scott.
All right. So unfortunately, the video is going to be. If you're watching the video from home, we're going to do a little hallway experiment. It's probably going to be about 10 minutes, so you might wait till you start to see the screen update again. Okay, but, okay, so if you're watching this video from home because you missed class today, we're now ready to start again. Sorry for the delay. Okay. Now, we do that little walking activity so you can get a visual sense and a physical sense of this. I'd like you to start with this drawing. So the one where I have a slow medium going to a fast medium and it hits it straight on into that interface. What would that wave look like when it travels from here to there, hitting it straight on? Okay, so try it. See if you can do it. If you're watching this from home, you weren't able to do the activity with us in the hallway, but it's to build a sense of how things change their wavelength and their direction when they hit at an angle. I'm hoping you guys can see that if the wave velocity increases, so it goes faster, the wavelength increases proportionally. If you go twice as fast, you'd have twice the wavelength. What determines the speed? What is it that determines, has the biggest role in the speed of the wave? The medium. So the medium has changed, went from a slow to a fast medium. What determines the frequency? What determines the frequency of that wave? Whatever it is, that's creating the disturbance. So if the disturbance has a frequency of 250 hertz, that's the frequency no matter where I look. So the frequency is determined by the source. So therefore, the wavelength is tied directly to the velocity. If the velocity changes, the wavelength changes, not the frequency. Now, if I go to a slow medium, I'm sure you guys have this. The visual models and the physical models are to help you sort of build a sense of this. But I'm sure that that's fairly straightforward, right? You slow down, the wavelength decreases, and you just travel at a slower speed. Now, the other one is a little bit harder to get. So the velocities decrease. There is an interface here, and I want to draw a normal line in. So normal, again, is important. We need to look at that angle. So the normal is perpendicular. Normal is the same thing when we call the normal force, right? It's perpendicular to the surface. So that's a normal line. This right here is called the angle of incidence. It's the angle that the incident wave, the wave that's coming into the interface, is traveling at relative to the normal. Now, can you guys, based on the little activity that we did on the hallway, can you predict which way that thing is going to bend? Like what would happen to those wave fronts? Will they lag behind or will they speed up? Will it bend toward the normal or away from the normal? Can you visualize it? I didn't draw these portions down here, but if I did, this portion of the wave front would have fallen behind, correct? Because it's sort of like lagging. It got into the new medium before the other ones. And so this portion here would sort of fall behind. If this one were a continuous wave like that, it would be like so. This portion here would be like that. And because the wave always travels perpendicular to the wave fronts, we would see that that would be the new direction. That would be theta r. And it would bend toward the normal. With the exact same kind of reasoning, if I were to draw in a vertical normal line here, and this portion of the wave has sort of gotten into that area before the other portion, it would sort of get ahead of the other portions, and you would sort of see that this thing would be traveling and bending like so. If this is theta I, this would be theta r. How much it bends and which way it bends depends on those factors. What's the change in speed? What's the angle at which it hits? Now there's an equation that's hidden down here and I'm going to share with you. This equation was developed experimentally by a gentleman named Snell. The sine of theta 2 is to the sine of theta 1. It could be the instant and the refracted or whatever, but the sine of theta 2 is to the sine of theta 1 as the velocity of 2 is to the velocity of 1. You notice that there's an angle dependence and there is a speed dependence. So both of those factors come into play. Now I'm going to show you really quick refraction with light. So this little simulation, it's a fat simulator. And for those of you that wear corrective lenses, your lenses are based on this kind of thing. I'm going to turn on a laser light for a second. And Luca, maybe you could grab the lights for me so it's easier for people to see. So this is laser light traveling in air, and here it's going into glass. I'm going to change that to water for a little bit, so it's an air-water interface. Now I'm going to show this in terms of wave instead of a ray. So what I have here is a laser light. It's composed of, it looks like plane waves that are going in here to change the angle of this thing. You notice that the angle that it hits the normal at, by the way, I think I can probably show the normals and so forth. Let me put this up here. That angle, if I were to go back to the ray, it might be easier to see. That angle there would be about 70 degrees. That's hitting the interface at. And then when it bends, it sort of bends down to an angle of about, it looks like about 30, maybe about 40, 45 degrees. I have a reflected ray. You notice that anytime I have a change in speed, I have some reflection and some transmission. Let's do a quick little, put this thing here as an intensity. If that's 100% intensity, then I can start looking now at how much light actually gets reflected. And there I see about, based on that angle, I get about 21.7% of the light reflected. The other must be transmitted because, again, energy is conserved. So all we're doing is we're basically splitting that light up. For those of you that do any water kinds of things, like if you fish and you wear polarized sunglasses, what polarized sunglasses do is they remove a lot of the polarized light that's reflected. And so that makes it easier to see inside that water. Now, the more glancing that angle, the more light actually gets reflected. You guys can't see that. But the bigger that angle is, you can see that the more of the light gets reflected and the less gets transmitted. Okay, let's do the wave model for a second. You notice that if it's a really oblique angle like so, I get a really drastic change in the direction of that wave. Okay. And so again, that's the idea of refraction. I'd like to do a problem or two with you. And so on this slide here, I can probably only get through one of these in the time that we have. We'll do our best with it. Lights off or on? You guys all still good with off? Okay. Light. In a vacuum, it travels about 3 times 10 to the 8 meters per second. It happens to be the speed limit of the universe. It's really close to the same speed through air. So air is really close to the speed for the light in a vacuum, 3 times 10 to the 8 meters per second. When it travels through water, it slows down quite a bit. It goes down to 2.2 times 10 to the 8 meters per second. Ray of light in air strikes an air-water interface at an angle 52 degrees to the normal. At what angle will it refract into the water? What will be the angle between the refracted ray and the partially reflected ray? So any of these kinds of things, we should draw a little diagram. That represents the air-water interface. Typically, we would draw a normal line to sort of visualize this because everything is measured relative to normal. The light's coming in. I'm going to use the ray model for this because it's far easier to draw rays than it is to draw wave fronts. So the laser light, or the light in this case, is coming in and striking the interface at an angle of 52 degrees. Can you tell which way it's going to bend? Can you visualize that if it slows down? Can you tell yet? If it were a wave front, this portion would sort of slow down a little bit here inside here, and it would sort of, it had to bend, it should bend towards the normal. Now, I'm going to draw that in. If you make a mistake, you'll see that the math will help you get that. I'm going to try to find that angle. Now, this equation, you're going to probably have a hard time memorizing it. It's not up there. So if you need it, I don't believe it's up on my stuff up there. It's not there. So you might need to like refresh your memory on this for test taking and whatnot. I'm going to get rid of this right here for a second. The way I like to think of it is if I'm looking for the angle of the refracted ray, I'm going to write that up top, sine of theta r. So sine of theta r is the thing I'm looking for. That is to the sine of theta I. That ratio is the same as the ratio of the speeds. So the ratio of the sines is in the same ratio as the velocities. Keep your r's or your i's in the same spot. Now just rearrange it for the thing you're looking for. I'm looking for the sine of the refracted ray, so theta r. So let's go ahead and solve that. Bring the sine of theta I to the other side. We're going to multiply that by VR to VI. Now, I'm writing VR to VI as separate by themselves. The reason for that, would you guys agree that that is a dimensionless quantity? It's going to be just a pure number. It's a ratio of two speeds. As long as those speeds have the same unit, then that should be dimensionless. I'm just going to take the ratio of those speeds. And then when I'm done, the sine of theta r is just the same as the sine of theta I multiplied by that value. So the sine of theta r. This is a sine of 52 degrees multiplied by the ratio of VR to VI. Now I'm going to do a little trick here for you. I don't care that they're times 10 to the 8th because aren't they both times 10 to the 8th? So I don't really care. These two things, when I take the ratio, those things are going to cancel right out. So it's really just the ratio of the coefficients of those numbers. So let's see, VR is 2.2 and VI is 3.0. And those are both in meters per second. You know, they're times 10 to the 8th, but those times 10 to the 8th are just enough. And so now you go through, you get the sine of theta r. Your calculator will give you that number. I got 0.579. So therefore theta r would be equal to the inverse sine of that. And you should get 35 degrees. So that light would bend to about a 35-degree angle. Now, I didn't do the other problem with my 6th hour. I'm not going to do it with you guys as well. We're going to save that for Monday. I just want to check that really quick just to show you. So I'm going to go back to my simulator here. Light traveling through air and light traveling through water are very common interfaces. So let's just go ahead and check that. Here's air, here's water. I'm going to make this angle. I'm going to put it into the ray model. What did we say the angle was coming in? Was it 52 degrees? Yeah. Okay, so there's 30, there's 40, there's 50, there's about 52. And then, let's see, the refracted ray we said was about 35. And sure enough, we can see that based on that there, it's bent at about 35 degrees to the normal. Now, the question that was asked in this thing was not just that angle. It was also what's the angle between this one and the reflected ray. So if this line comes in at 52 degrees, how does it go away? It goes away at 52. So could you determine this angle? Could you look at your drawing and determine what that angle is there? I think you can. Really, that angle that I'm looking for is this one here. That light comes in and it reflects like so. That angle is 52. So really what I'm looking for is, I'm going to call that beta. What is that angle? And your supplementary angle idea is that if the total has to add to 180, you take 180 minus 52 minus 35, and that would give you that angle. Okay? Cool. There's a lot of things that waves can do that particles cannot. We've just looked at reflection. They behave differently based on what kind of interface we have. And they also refract. Particles do not refract. So those are properties that are wave related. I'm going to go ahead and stop this thing here.